All right, welcome back to Speed, Math, and CS. Today, we are going back to AP Physics C, Electricity and Magnetism, and today we're starting on Unit 4, which will be simple resistor and battery circuits, right? I know the past couple of units have been quite the predicament. They are filled with the vocab, and usually they are the most difficult ones out of this. But today we're going to be taking a break. We're going to look at something easier, something at least for me was more fun to learn, right? We're going to be experimenting with how we solve circuit equations and things like that. But to start off, right, we'll start by going over the definition of electric current. So of course, this unit is going to be all about current and how it interacts with resistors. So it's good that we first start by defining it, right? So current, as we defined in the very first lesson, right? Current is equal to the derivative of charge, right? With respect to time, right? This makes sense because charge has the units of coulombs, right? And current has the units of coulombs per second. So remember, whenever we take the derivative, we always sort of divide by a variable amount with whatever variable we're taking the respect to. So this makes sense as to why it would be the derivative. So, and coulombs per second, we also have a second unit where we measure it as amperes, right? This is the more common SI unit that we're going to be using. And this, right, because it's a derivative, this is the instantaneous current, but there is also average current, right, which is the same formula we learned from calculus, right? So average current will be equal to delta Q. Oh, it's not. Give me a sec. Yeah. Delta Q divided by delta T. So something like so, right? Because remember, if we're taking the average, right, we will just use the delta, right? Because this represents the bounds of the integral we would otherwise take. So now that we've defined essentially what this means, what current essentially is, right? It's the total electric charge which passes by a point over a time period. And current only forms when, let's say we have, so let's say we draw out a circuit here, right? We'll say this is a battery for now. We'll get into the formal notation later. But let's say this is a battery, right? And then we are hooking it up to some wire, right? If there's no potential difference throughout the circuit, right, the electrons inside of this wire are just going to stay in place. They only want to move if there is a potential difference, which we'll see in batteries, right? There is a positive side and a lower side, and in conventional current, we go from high potential to low potential. So potential difference is defined as delta V, which we learned in the first unit as well. And if delta V is equal to 0, we know that current is also equal to 0, right? And the direction of conventional current, like I mentioned, is the direction in which positive charges would flow, right? In reality, remember that it's really electrons or negative charge flowing in the opposite direction, but we're gonna treat it like conventional current because this is what you'll see on the actual AP exam, and we will be flowing as if they were positive charges, right? So if we take a look at if we zoom in on this wire, right, it'll actually look a lot like a cylinder, something like so, right? And inside the cylinder, we'll have various electrons, right? Yes, like so, right? We'll have various positive charges. And essentially, if we take a cross section of this wire, right? For example, like so, current can be measured by the number of coulombs of charge that go through this small cross section. So essentially delta Q, right? Delta Q in this case will be defined as the total charge which passes by a point during delta T. Therefore, this proves our formula from earlier, where the average current is equal to delta Q over delta T, right? So delta Q can also be written as, in this case, delta Q can be written, delta Q can be written as equal to the number of charges, right? Or in this case, let's draw it as N, multiplied by the charge per carrier. So essentially, the charge per carrier will just be Q. So, yeah, something like so. And then, in this case, right, if we want to break down what this N would be, the number of charges, right? So N is equal to the number of charges, right? Number of charges divided by the volume of the wire. So in this case, we're taking this cylinder, so the volume of the cylinder, right? So volume. Just so we don't confuse it with the potential, I'll put a small subscript there, like VO, right? So this essentially means that if we want to get to the number of charge carriers, like actually this will be a capital N in this case, right? The number of charge carriers, if we just want to isolate this top, right, which will be capital N, right? Capital N is also equal to N times V, right? So we can actually simplify this formula into the number of charges multiplied by the volume multiplied by the charge. So now what we're going to get into a concept called drift velocity, right? So if we look back at this wire here, right? For any given electron, right? Drift velocity is the average velocity of all those charges, right? So once again, if we're taking average velocity, right, is an integral of velocity. And to get from position to velocity, we differentiate. So in this case, we're just going to be there's not going to be any like integration or differentiation. We're just going to be using the same delta that we used for average current. So drift velocity, or we'll do this as V with a D subscript, right? I know all these V's can can be very confusing, right? We have potential as a V, velocity as a V, and then volume as a V. But we'll find some way to differentiate between them. But essentially, yeah, so drift velocity will be denoted as something like so. And this is equal to delta position over delta time. And this is like each electron will move slightly differently, right? Just like from our example from earlier in this like circuit, which is like a short circuit, right? The electrons will be moving slightly, but the average velocity of all the electrons in the circuit will be 0. So now with drift velocity, right? Drift velocity is typically very low, right? And basically the velocity of electrons will be mostly based off of current. And if we wanted to isolate delta X here, we could do the same thing, right? If we're trying to isolate delta X, this will be equal to drift velocity multiplied by delta time. Something like so. So if we go back to our equation for delta Q, right? We can replace volume in here with just the area of a cross section, right? Because it's hard to find the volume of the full wire when there's twists and turns, right? So we can simply say this is equal to the number of charges multiplied by the area, or I don't know why I drew a triangle, multiplied by the area, which is denoted as A, multiplied by the drift velocity, times delta t, right? This is what we derived for delta x, right? Remember, volume can be broken up into, from our integral formula, this can be broken up into the area of a cross section multiplied by delta x. And because we isolated delta x up here into drift velocity times delta time, we can simplify it as so down here, right? With values we'll know. So, and lastly, we multiply by charge. So this looks like a pretty complicated formula so far for the change in charge. But essentially what we will do to define such, in order to define such in forms of current, right? Remember, average current will be equal to delta Q over delta T, right? So right now, at this point, we have been solving for what delta Q is, right? So at this point, we've been solving for what delta Q is. But now if we want to solve for actual current, this is how we would do it. We would simply take what we had up here, right? This would simplify to N times A, or number of charges times area times drift velocity times delta T times charge, all over delta T. And in this case, right, we can cancel out the delta T, and that is equal to the number of charges multiplied by area multiplied by drift velocity multiplied by Q, and or charge. So this is the formula for charge. And this is what we're going to be using to solve for later equations. So charge will look something like this. And now if we wanted to solve another concept, right, is something called the current density, right? And as like someone could guess, right, the current density is essentially if we took a cross-sectional area, right, the current passing through that divided by that cross-sectional area is the density across that area. So that is going to be our current density, right? And it's going to be defined by a letter J. So it's going to be J equals to current divided by area. And if we take the same formula from earlier and we plug in what we already have for current, right, which is equal to number of charges times area times drift velocity times charge, and then divided by area, this is going to be equal to the number of charges times drift velocity times charge. So this is going to be our current density function, right? And essentially, in order to solve for our next equation, which will be Ohm's law, which will help us determine the resistance and also help us determine current, right? We can actually simplify this current density equation into J equals to the area charge density multiplied by the electric field, right? We saw an equation similar to this in the very first lesson, right? So now moving on from this, right? This is one version of Ohm's law. J equals to current charge density, right, multiplied by electric field, right? And in this case, this current charge density, we will be referring to it with a new name, and that is going to be conductivity. And essentially, conductivity is a measure of how how much a material allows the electric charge to push through, or another meaning, right, which we use to define resistivity, how little a material opposes the actual charge movement, right? And conductors that follow Ohm's law are called ohmic, and conductors that don't follow Ohm's law are called non-ohmic. On the actual AP test, all of the resistors and circuits will follow Ohm's law, or in essence be ohmic. So there's no need to worry about this for now. And like we covered earlier, an electric potential difference across the wire is what actually causes the current. Remember, current as we defined here is the number of charges through an area multiplied by the drift velocity multiplied by the charge. If we take this thing of current, right, and there's no potential difference, that means that this drift velocity is 0. And because this current is made up of 4 factors, and any one of them becomes 0, then the whole current becomes 0. So if there is no charge in the current, there's no current. If the wire is infinitesimally thin, there's no current as well, right? And essentially, looking back at the circuit, right, the only reason the electrons will move is because there is a potential difference. Remember, positive charges like to go from high potential to low potential. If there's no battery, right, which is essentially serves as a chemical device to increase the potential, right, there will be nothing forcing the current to actually move through the circuit. So essentially, so assuming the electric potential difference across the wires, what actually causes the current, right? And assuming that the electric field in the wire is uniform, right? This is what builds upon all of our laws that we're going to study, right? So, sorry. So then the potential difference, so potential difference can be defined as the electric field multiplied by distance. Remember this, we also learned this formula in the very first unit, right? This is where we put all those first formulas we learned in the first unit into actually action and getting into new laws, right? So if we do something like this and then solve for electric field, in this case, what we can do, because we're using distance here, and this is a circuit, we'll replace this D with an L, right? This L will be the length of the actual wire we are considering. So essentially, if you solve for the electric field, right, the electric field equals to delta potential divided by length. And because you can see here why the electric field has to be uniform, right? Because the potential difference across the circuit is always uniform. The length of the wire will be uniform. We're not changing either of those, right? So in this case, we have to assume the electric field is essentially uniform. So now let's actually use this to solve further, right? So we know that electric field equals to the actual energy divided by the conductivity, right? So we can simplify this into joules, into the current density, right? We know that by Ohm's law, right, we know the current density is equal to the conductivity times the electric field. So we can actually simplify the equation like so. We'll use conductivity and multiply it by this expression here. And then now if we solve for the delta potential, right? Solving for delta potential gives us that current density multiplied by conductivity multiplied by length is equal to the delta potential. Or no, sorry. Not multiplied by. the divided by the conductivity will be, I know that, oh, that's a very sloppy drawing of the row, but that current density times the length of the actual wire divided by electric conductivity will be equal to the delta potential, right? And as we know from earlier, right, we can actually replace this J in here with an I. So this will simplify to current times length divided by area divided by conductivity equals to the delta potential. And in this case, right, we have a formula here, right? Length divided by area times conductivity. If we isolate this section of this sort of product here, right? This is what we call the resistivity of like a resistor, for example, or just in general, the resistivity of the circuit, right, is R. So we can actually simplify this to I times R. So now we have a much more applicable form of Ohm's law, right, where V equals to IR. And right here, this is going to be a golden rule for solving circuits. So, yeah. So now going on, right? The resistivity or resistance is in the form of ohms, right? Which is volts divided by amperes, right? And essentially, if we look at this formula from earlier, right, with conductivity, we can actually replace the conductivity. 1 over conductivity is actually something we will call resistivity, and it will be used, and we will represent this through the rho. Don't confuse this with volumetric charge density. It is the same symbol. So we can replace it with something like so, right? So we just move this conductivity to the top, right? And resistance has units of ohms and is the property of an object, right? Resistivity has the units of ohm meters and is the property of the actual material in the resistor. So two objects can have the same resistivity, right? They're both going to be made up of, like, let's say rubber. They're both made up of rubber. So they're going to have the same resistivity because it won't differ from the same material. But they could be longer or they could have larger areas. So if we actually analyze this, if we actually break down this new form of resistance, right? If the resistivity is higher, this means that the material naturally stops charges from coming through, right? It naturally slows down charges. And if the length is larger, right, the resistance is longer. The charges have to go through more resistance to actually get through. The reason area is on the bottom is because the bigger the cross-sectional area of the resistor, the more paths that the actual current can take. So, yeah. So this will be the formula we use to evaluate the resistance of a resistor. And the resistivity of a conducting material, right, isn't just based off of the material itself, right? The resistivity of a conducting material typically will decrease if it gets super cold, right? And superconducting materials typically will have zero resistivity and require very, very low temperatures. So things like wires are very conductive. And unless otherwise stated, on the AP exam, right, the resistivity of conducting materials is considered to be constant regardless of the temperature. We assume temperature to be constant on the actual AP test, right? And resistors usually convert the electric potential energy to thermal energy. So this will cause the resistor to get pretty hot as charge goes through it. And it'll increase the temperature of the resistor's environment. So now, one final vocab term before we get into actually looking at circuits. So another term we learned was electric power, right? Where electric power is defined. Sorry, it's not dry. Yeah, is defined as the derivative of electric potential energy with respect to time, right? So power has the units of joules per second. And what we can notice, right, is that in order to get to joules per second from the units of potential, which is joules divided by coulombs, right? We have to multiply by the coulombs and multiply by the seconds, right? Which immediately should ring a bell, right? If we have to multiply by coulombs, divide by seconds, this means that we have to add current somehow. And we can actually extend Ohm's law like this, right? Power will be equal to current squared times resistance, right? And of course, there's many ways to write this. You can write this as the electric potential difference multiplied by the current, or you could write it as the electric potential difference squared divided by resistance. But there's multiple ways that we can write this. But essentially, this is how we consider power, right? And another thing is typically we will look at things like kilowatt hours, right? Which will be like kW times hour, right? So essentially kilowatt hours, these are the units that we typically, if you look at a machine at home, this is the units they'll typically use, right? So it's very similar to what we have been using, except it's 1,000 watts. Yeah, 1,000 watts times 3,600 seconds, right? So as you can see, this kilowatt hours are lower than joules per second by a factor of 36 or 3.6 million, right? So by a whole lot, right? Because typically joules per second, joules are super tiny units. So if you look at a machine, right, they will typically be used as they'll typically use this because it'll be a much smaller number. It's much smaller to say 6 kilowatt hours versus 21.6 million joules per second. So it's essentially that's what it would be like. And additionally in circuits, right, we've already talked about resistors, right? If we take this simple short circuit from earlier, right, we can add a resistor, right? So for now, I'll be using boxes, but we'll get into the formal notation soon, right? So we'll have a resistor here, but additionally, we can also add a light bulb, right? Because typically circuits are used to light bulbs, right? And essentially, a light bulb, it can be treated as a resistor, right? Which can instead of a resistor which converts that electric potential energy to heat, right? Or essentially just resist the circuit, right? The light there's many different types of light. First, an LED will convert the energy that goes through it directly to a light. So it'll take the electric potential energy, convert it to radiant energy, right? And incandescent bulbs can also convert it into heat energy, right? So it can heat up, it can serve as double purpose, right? So, and it's often used to demonstrate the power through a circuit, right? So to our eyes, we can't really see what current's going through. So typically we can stick a light bulb. The brighter the light bulb, the more the current, so the less the resistivity and things like that. So essentially, another the last new unit, right, is going to be what we call electromotive force, and it'll look something like this. I know they essentially ran out of Greek letters, so we had to reuse the one that we use for E naught, which is the permittivity of space. So remember to not confuse these. So electromotive force is actually, it's not a force, right? It's a misnomer, right? And it's essentially the ideal electric potential difference or voltage. And the batteries are typically marked, like when they're marked at 3 volts, that's like the electromotive force, right? So that's going to be like the potential difference across the battery. Yeah. So now let's get into the notation we'll actually use to like draw out a circuit, right? Let's get into actually the fun part now. We're going to be drawing out circuits. So we will, at least for a battery, right? We're going to be using something like so with 4 bars, something like this, right? That is what going to be what a battery is represented by. And then on the AP test, right? It's not going to say, okay, 3 EMF. It's just going to say 3 volts. And that's the electromotive force. So essentially, how much the potential difference across this like this wire, right? Across the battery. So this is the positive end, this is the negative end, right? So essentially, positive charges will be flowing into the wire like so. Like that's a positive charge. It's going to be flowing into the wire at, let's say it'll have like 1 volt, right? It doesn't matter how many volts. So typically we'll just set the end to 0. Because remember in the first lesson, we learned that the actual electric potential doesn't matter, solely the differences in potential. But let's say we have a charge that's coming in at 1 volt to this side, or at 1 like voltage on this side, right? Essentially, the electromotive force of this battery is 3 volts. So when this electric charge passes through the wire, on this side, it's going to end up with the electric potential of 4 volts, right? It's not letting me, 4 volts. So essentially, the battery is a chemical device which uses electromotive force to essentially increase the potential of charges. And then, so yeah, this is the double cell battery, right? This is what is typically going to be used on the AP exam. But if you see something like so with like something like this, that is like a single cell battery. Something like so. So something like this will be a single cell battery. We'll usually not see this. We'll usually see a double cell battery because that's what we use in household appliances nowadays. We just use double cells. So, and then a resistor, right? Let's say so let's say we have like a resistor in the circuit, right? So what a resistor is going to look like is essentially going to be a dashed line going, it's not drawing. Yeah. So something like so. It's going to be like a dashed line like this, and it's going to be marked like, so a resistor is going to look something like this, right? It's going to be like that and have a dashed line like so, and it's going to be marked with a resistance. So for example, 3 ohms, right? And then using methods we'll focus on later today, right? We're essentially, as a charge passes through this resistor, its potential will drop. So let's say it's at 4 volts now. Now it'll go down to like 1 volt, right? So as it passes through a resistor, the potential drops, as according to Ohm's law, right? So we'll take this resistance of the circuit will be important, right? So remember that delta potential equals to I times R. So let's say the circuit, the current flowing through was 4 amps. Or yeah, sorry. At least for the concern of this example, right? Let's say it says 1 amp, right? Going through this, right? 1 amp, if the current is 1 amp going through this and it's at 3 ohms, right? If we take the current, right, 1 amp multiplied by 3 ohms, that'll be 3. Meaning that the potential drop across this resistor will be 3 volts, right? And let's say we were given a problem. Like, this could be a possible problem. Let's say we were just given the circuit like so, and we had to solve for amps. Like, let's say we were not given this. Let's just say that the we knew that but yeah, let's say we weren't even given any of this, right? Let's say we know that this is 3 ohms, and then the battery increases the current by 3 volts, right? So as per what we learned in the first unit, right, we can set anywhere to 0 volts. So let's set this negative side to 0 volts, meaning that it'll be at 3 volts when it passes through here. Remember, our goal here is going to be to solve the current passing through. So, for example, this current passing through is going to be, let's just say IA, right? So this is going to be the current passing through. We're solving for this, right? So we know that in order to be at 0 volts at the end of the circuit, it doesn't just lose potential as it goes through the wire, because the wire has negligible resistance. So we know that the potential drop across this resistor has to be 3 volts, right? Because how else would the potential get back to 0 volts? So if the potential drop is 3 volts, we plug that in here. Resistance is 3 ohms, plug that in here. We solve the current is 1 amp. So this is essentially, so this will be 1 amp, right? So this is what a typical problem like so will look like. So now let's get into actually drawing more circuits, right? So let's start with putting for now we're just going to be concerned with batteries and resistors, right? So let's draw another circuit, right? With the battery of, let's say, 3 volts again, because 3 volts is the typical like snap circuit type voltage. So let's say we had a resistor. We had two resistors in series, right? If we have 2 resistors in series, and this one is 4 ohms, and this one is 1 ohm, right? Essentially what we can do is we can essentially we can simplify our process, right? Because typically, if you think about it, right, the charge will go through, experience some potential drop across this one, go directly into the next resistor, experience a proportional potential drop with the 1 ohm. So, in fact, as per Ohm's law, if we have resistors in series, we can essentially combine them into, let's erase this part. We can essentially combine them into one big resistor of 5 ohms. And then now we don't have to do the weird thing where we consider potential drops. This is only alluding to what we're going to cover when we get to Kirchhoff's laws, right? But essentially, with this, right, we can directly solve for Ohm's law using what we have here. So Ohm's law says what? Delta potential equals to I times R, right? And let's say in this case we're solving for the current, right? So we're solving for I1, right? Essentially, so we can plug this in, right? 3 equals to I1 multiplied by 5. So solving for I1, we get that the current is going to be 3/5 amps. So this is how we treat resistors in series. But let's say now we have resistors on 2 separate wires like so, right? So essentially, if we have something like so, where we have one resistor here, and then there's a break in the wire, meaning that electrons can go here or go here, right? Something like so, right? Where they're on 2 separate wires. We had the battery just like so, up here. So yeah, so the battery here will be 3 volts. This resistor could be like 2 amps. And let's say that this one was also 2 amps. In this case, we can't just combine this resistance because in this case, the electrons will essentially flow to whichever one they seem is easier. So for example, if this resistor was 1 ohm, actually that's actually better, right? Let's say this one had less resistance. About 2/3 of the electrons will head into this 1 ohm resistor and get resisted by 1 ohm amount, and 1/3 of the current will go into the second resistor and experience 1/3 that amount. So essentially, if you think about it, right, in order to do this, right, since the current is taking the lightest path possible, we have to convert this ohm into a thing called Simons, right? And Simons are going to be used to represent conductivity, right? So Simons are just going to be 1 over ohms. So essentially, this is going to become 1/2 Simon, right? And then 1 over 1 is just 1. So this is just going to, 1 ohm is the same thing as 1 Simon, right? So Simons are the notation for conductivity, right? And because conductivity represents how light it is to pass through either one of these, at this point we can combine both of these conductors into one big conductor. And because that one had 1 Simon of conductance and this one has 1/2 Simon of conductance, right? This will become, so this will become 3/2 Simons. So now that we have 3/2 Simons, right? So using this 3/2 Simons, we can convert this directly back to resistance. So this is going to just become 2/3 ohms. 2/3 ohms. So that helps us solve for resistors in parallel. And as you can see, because the electrons are finding the lightest way to go through both the resistors, when you have 2 resistors and put them in parallel, that actually reduces their overall resistance. So typically, let's say you only had, typically parallel resistors in terms of appliances are used when you're trying to achieve a fractional resistance, but you can't do that unless you go through and actually combine the combine resistors in parallel, right? So you only have 1 ohm resistors or 2 ohm resistors, but you're trying to get like 2/3 ohms of resistance. So sticking resistors in parallel is how you would do this. So essentially, for a formula, right? Resistors in series are super easy. You just add them up. But in parallel, right, we'll have a formula, right? Where resistance will be equal to 1 over conductance, right? The overall resistance is equal to 1 over conductance. Simplifying conductance down, right? Conductance is equal to, if we have 2 resistors in parallel, right? The conductance is equal to the conductance of the first one plus the conductance of the second one, right? Going even further, we can simplify this conductance to be 1 over the resistance. R1 plus 1 over R2. Yeah, so on and so forth, right? So 1 over like R2, right? And you could do this for any amount of resistors. But essentially what you're doing, you're taking 1 over the resistance, adding up all the conductances, right? So that'll be all the 1 over resistances, and then you're adding them all up and taking the reciprocal of that to get the overall resistance. So resistors in parallel are a bit more complex, but this is simply how it works. And essentially, the strategy is, right? is that if you have more complicated resistor arrays, right? What you're gonna do to calculate the equivalent resistance, right? That's mostly what Ohm's law deals with, is finding the equivalent resistance. So you're gonna identify a small isolated group of resistors that are in series or parallel, right? So for example, if you have a bunch of resistors in series, you can just add them up. And if you have a bunch in parallel, you just add them up again, right? So, yeah. So essentially, the thing is, right, that you always want to start with usually you'll want to start with the resistors in parallel, right? Treat the parallels as sort of brackets containing them. You always want to go from the smallest group that isn't consisting of larger ones to the whiteboard is. Yeah, sorry. Yeah. So essentially what you're going to want to do is you're going to simply just want to take the smallest group of you have constant resistances, combine them, and then redraw it out with that updated resistance. So essentially, let's do a problem, right? Yeah. So let's say we have let's draw out a circuit actually. Or well, I don't know why I'm still using boxes. But essentially let's draw out a circuit, right? Where we'll have the battery down here. But essentially we'll start with 2 ohm resistor, right? 2 ohm. Right? And then we'll have a 3 ohm here. In fact, we'll actually have to extend this wire a bit. But yeah. And then let's say this connects to a thing up here where we have 2 ohms, a 2 ohm resistor up here. This looks a bit messy, right? But and then we have a 7 ohm resistor here, and then actually let me move all of this down. Yeah, let's move all that down. And then let's say you had like a big 25 ohm resistor up here, right? So the first thing we can do, right, to start combining stuff is we can consider that we have a tiny parallel. So first we have 2 sort of resistor arrays in series. We have this 2 ohm resistor and whatever the resistance of this big array would be, right? Inside of this big array, we have 2 things in parallel, right? We have this 25 ohm resistor in parallel with the 2 ohm, 3 ohm, and 7 ohm, right? Inside of this parallel element, we have a parallel 2 ohm resistor and 3 ohm resistor and a 7 ohm resistor that's in parallel with this. But the 2 ohm and 3 ohm resistor that are in parallel looks like our smallest piece that we can actually start with. So let's start with that. So if we take a 2 ohm resistor and a 3 ohm resistor and solve for the resistance, right? Resistance equals to 1 over 2 plus 1 over 3, right? Which would be equal to 1 over 5/6, which equals to 6 over 5, right? So we can simplify, or in this case, it would be 1.2, right? We could simplify the circuit down to down to a 2 ohm resistor, right? Two ohm resistor, and then now we can start with this parallel component, right? Where we have, or no, sorry, not this parallel component, right? Now, at this point, this has been simplified into a 1.2 ohm resistor, right? That is now in series with the 7 ohm resistor. So those two will combine into an 8.2 ohm resistor. Something like so. 8.2 ohm resistor. Right? Something like so. And essentially, now with this, right? With these two, because they are parallel, for this you'll need a calculator probably, but resistance equals to 1 over 25 plus 1 over 8.2, right? $8.2. And essentially, with this, right, if we solve this out, right, we'll, in your calculator, you'll get that this resistance is equal to 6.17 ohms, right? So then now we will essentially simplify this down to a 6.17 ohm resistor, this entire array, which is now in series with this 2 ohm resistor. So essentially, the overall resistance is just going to be equal to 8.17 ohms. Hopefully, now with this example, we have a very clear way to solve Ohm's law's equations. So now let's move on to the next part of our lesson, right? So just for some quick vocab, right? So essentially, voltmeters and ammeters, right? So this will just be more like just me lecturing for real quick, right? So in order to measure like voltmeters and ammeters are essentially things which humans will like stick into the circuit. Like for example, you'll stick a voltmeter like this, right? Voltmeters are always stuck in parallel. So we'll stick a voltmeter into here, and then ammeters are always stuck in series. So an ammeter will be stuck like that, right? So for voltmeters and ammeters, right, in order to measure voltage, right, a voltmeter like so will be attached in parallel across the resistor or some other circuit element whose voltage it is measuring, right? So essentially, let's say let's say we have a voltmeter across this resistor, like so, right? A voltmeter like this. That voltmeter will measure the potential drop across that resistor. And because elements in parallel exhibit the same voltage, the voltmeter essentially is able to measure the voltage of the element it is connected to across. In order to make sure that the addition of the voltmeter doesn't actually affect the circuit, the voltmeter is designed to have super high resistance. Like we're talking like millions and billions of ohms, right? Because they only really need a tiny little piece of like electron to come through to get their value, right? And essentially, what this can help us do, right, is this can help us, like this is the first technique that we used, right? So this can be used to solve for the current, right? So the voltmeter will tell us the potential drop across this resistor. The resistor has some ohms. Using Ohm's law, which is V equals to IR, right, we can solve for the current. But now, later, scientists invented a new technology called an ammeter, right? So an ammeter, right, simplifies this whole process of using a voltmeter. Of course, a voltmeter is still used today for many different purposes. But now, in the case of trying to solve for current, right, we have an ammeter. So the ammeter is inserted in series to the wire whose current it is measuring. And because elements in series have the same circuit, the current flowing through the ammeter is the same as that's flowing through the circuit elements, right? Because remember that if we have electrons like so, right? Or sorry, yeah. Or we don't need electrons actually for this, right? If we have some current that is flowing through the wires, right? Because of the law that electrons that are slow over here will not be able to push the fast electrons. So the electrons will be slow. So the thing is, it's not like the current over here is faster than the current coming in through here, right? So essentially, the current across the whole circuit is the exact same. And this current is essentially representative of the total resistance throughout the circuit. So even if electrons over here haven't experienced any movement, they're going to be slowed down by like sort of the traffic ahead caused by the resistors. So the current is the same throughout the entire circuit, except for in branches such as so. When things branch off like this, current separates. So this will get us into Kirchhoff's law, right? So the ammeter is essentially, super low resistance and just directly measures the current. Now, let's get into Kirchhoff's laws. So, essentially, Kirchhoff's laws will help us, more complicated circuits, right, that contain more than one battery can't always be solved using Ohm's law and equivalent resistance formulas. Kirchhoff's law provides a methodical way to solve such circuits. And essentially, the thing with this is we will be creating loop equations, right? So, essentially, we will use the same thing as algebra, where you're going to need the same number of loop equations as the currents you are solving for. And Kirchhoff's laws are used to solve for the current through a circuit or through different wires, right? So essentially what the two rules are, right, is essentially add a node, right? And to solve these will essentially be like equations. We will solve them like equations. So the first one is the node rule. So add a node, right? The current flowing in is the exact same as the current flowing out. So essentially, the sum of all the currents coming in, the sum of all the currents in each of these four wires is 0. And the second equation is the loop equation, right? So if we take a certain loop of wiring, right, and then we sum up all the potential drops will sum up to 0. So let's do an example. Just that Kirchhoff's laws become easier with examples, right? So essentially let's actually do So let's do an example like so, right? So let's think of a circuit like so, right? The best way to do Kirchhoff's law and understand it is just by going through an example, right? So let's say we have a circuit like so, right? We have a battery like so, right? 10 volts. And then, right, it's split up down here, right? Into a 20 ohm resistor, here we're going to have a 10 ohm resistor, and then up here we're going to have a 10 ohm resistor, and then up here we're going to have a 20 ohm resistor, right? They'll all connect like so. And we're asked to, let's say we have some current like so, right? So, like so, right? The current, we're tasked with finding the flow of current in this direction. What is the flow of current in this direction? So let's start by actually defining the currents we will need in order to solve this Kirchhoff's law problem, right? So the first current we can calculate, we'll label this I1, right? Is just the current going over here. This is I1. The second current will be the one coming out of the wire like so. So I2, right? The third current will be the one going through here, right? Because at this node, it splits off. So I3, right? And then the next one will be over here, which is I4, right? Because I3 will split off at a node here, and then I4 coming through here, and then essentially here, let's call this I5, right? I5, right? I2 will split up into I3 and I5, right? I5 then splits up into, let's call this one I6, right? I6 going this way, right? So it'll split up into I6, and then let's call this one I7. So that's a lot of currents we need to solve for in order to get our final answer. So let's actually draw all these equations, right? Let's make a list of Kirchhoff's law's equations in order to solve this. So I1 and I2, we'll notice, are on the same value, and they're only going through a battery. So they're actually going to be equal, right? I1 is equal to I2, which means, in fact, we can actually save ourselves the hassle. We can save ourselves the hassle and just get rid of I1, right? So now we have only 5 variables we're gonna solve for now. So, we have 6 variables we need to solve for. So it's always crucial that you want to reduce the number of equations you have, right? So the first one we can think of is a node equation, right? So at this node, I2 splits up into I3 and I5, right? So we know that I2 equals to I3 plus I5, right? And then now if you look at I3, for example, I3 is splitting up into I6 and I4, right? So, or actually, in this case, right, I6 and I3 are combining into I4, right? So I4 actually equals to I3 plus I6. And then now if we're thinking of, now I4 and I7 combine into I2, right? I2 equals to I4 plus I7, right? And that, I think that's no. We can have one more node equation. I5 splits up into I6 and I7, right? So as you can see here, we have 6 variables and we already have 4 equations. So as we learned in algebra, the number of variables you need to solve for is the number of equations you need. So in this case, using Kirchhoff's node rule, we have made ourselves 4 equations. And now let's use Kirchhoff's loop rule to make the next set of equations. So we can actually make 3 loops, right? So the first loop is is, let's say, let's consider this loop to be the first one, right? So with our loop equation, we know that 10, and loop equation is looking at potential drops, right? So 10 volts, right? 10 volts is equal to I5 multiplied by 20, because this is using V equals to IR and superposition, right? Plus I7 times 10. Remember, because I5 is the current going into this 20 ohm resistor, I7 is going into this 10 ohm resistor, and we're considering this loop, right? So we've made this equation. Now let's consider another loop, right? Let's consider I3. Let's consider this top loop up here, right? So now we have that I3, I3 equals, what did I do wrong? Oh, yeah, sorry. Wait, what do we mess up here? Oh, yeah, sorry. Yeah, I3 times the 10 ohm resistor equals to I5 times the 20 ohm resistor. So the potential drops here is a result of I3 going into here. That's a potential drop. And then negative I5 going out is a potential drop. So we now have this equation. And lastly, we can also make another equation with this, right? Where the potential drop in this loop must be equal. So we can once again say that I7 times that 10 ohm resistor equals to I4 times that 20 ohm resistor. Yeah, times that 20 ohm resistor. So essentially now what we have to do is we just have to solve for I6, right? I6 is what we were given in the original problem to go solve for. So now let's try to substitute into, like, we have like 7 equations here, but we're just trying to solve for I6. So I6 is given in this equation, right? I6 equals to I4, I6 plus I3 equals to I4. So I4 is given here as being equal to I7 times 10, and I3 times 10 is being equal to I5 times 20, right? So I5, essentially what we can do is because we have that I5 20 plus I7 10, right? Two things here are being equal to 10. All we have to do is simply substitute I4, right, is equal to, solving for I4, we get that I4, so if we solve for I4 in this equation, right, we get that I4 equals to 1/2 of I7, right? And solving this equation, we get that I3 equals to 2 times I5, right? So now if we substitute that into the equation up here, right, we have that, so we have that 1/2 of I7 is equal to 2 times I5 plus I6. And essentially now what we can do is if we isolate I7 and I5 on one side, right? So if we solve for the if we use this equation to solve in for I7, I5, and I6, right? We'll get that I7, right? I7, which is equal to the sum of I2 minus I... Sorry, what did I put here? Yeah, we'll get that I7, right, is 0.25 amp, right? So we'll get that this will be 1.25 amp, right? And this we get by plugging in that 10 from the other equation, right? That's what we'll get. We'll get that 0.125 equals to 2 times I5, right? And in our case, right, I5 is this wire right here, right? So this wire right here we already solved as 0.5 amps, right? So essentially, yeah, so this will become 1 amp overall. Yeah, so sorry. This is going to be 0.75 amp, right? Plus I6. So then now if we solve this, we get that I6 equals to negative 0.25 amp, which means that in this case, the I that we were solving for actually goes in the reverse direction. So the I actually goes in this direction, right? So remember at the start we were solving for I, right? Which is flowing in this direction, or like so. So what it means by our answer that we got for I, for this problem, which would be negative 0.25 amp. That means that essentially the current is flowing in the opposite direction at a current of 0.25 amp. So yeah, I hope this review was helpful for you, and yeah, we'll see you in the next one.